Have you ever wondered why it's easier to push something up a ramp than to lift it straight up? Or how tension in a rope keeps a bridge suspended or a mountain climber safe? Behind all these questions is the idea that forces are vectors, and just like in the last lesson, we're going to use the ability to break these vectors into their component x and y parts and then combine them into one resultant vector. The ability to do this allows us to take the messy, multidirectional forces of the real world and reduce them to clean, solvable equations. By the end of this lesson, you should be comfortable tackling ramp and tension problems and understand how the same math that keeps bridges standing, elevators moving, and roller coasters zipping along safely can be used to solve day to day calculus and physics problems. We're going to tackle all of these problems the same way. We're going to make a diagram or draw what we would see if we were to draw a picture of whatever the word problem happens to be. Once we've done that and we've got ourselves situated with where all of the vectors should be based on the drawing, we're either going to break it into components, into the x and y components, and use SOHCAHTOA and work with the vertical and horizontal components separately. So imagine I have one vector that's maybe at 20 degrees and another vector that's at 60 degrees. If this is force 1 and this is force 2, remember I can break this into fx1 and fy1 and fx2 and fy2. And once I've done that, then I can add fx1. So all my force in the x direction will equal fx1 plus fx2. All my force in the y direction will equal fy1 plus fy2. That will give me some other two new vectors. And then I can take my y vector and my x vector. Actually, we'll add them tip to tail. So I can take my x and my y, my new x and y's, add those together tip to tail, and use that to get my resultant vector. Or we could redraw the vectors as one triangle, tip to tail, with the angles. This takes a little bit more of geometry maneuvering to figure out what these angles are, and then use the sine law, the cosine law, and a combination of SOHCAHTOA to figure out the magnitude and direction. We need to remember that to determine both the magnitude and the angle or the direction. When you see angle, that really means the direction. So, like we always do, let's start with an example. We're going to start by looking at a typical tension problem. So we have a 10-kilogram object suspended from a horizontal ceiling, and it's being held up by two ropes. One of them has an angle of 65 degrees with the ceiling, so this one here, our rope number 1, and the other one has an angle of 42 degrees with the ceiling. And we can see here is the sign, and it is being pulled down by this Fg, or force of gravity. So tension is the pulling force inside a rope, a string, or a cable. And if a rope is holding up a sign, the rope pulls up on the sign, balancing out the force of gravity that's pulling it down. Now, those of you that have taken physics understand that according to Newton's second law, force is equal to mass times acceleration. But we need to know what this acceleration is when it's the acceleration due to gravity. And the acceleration down due to gravity, we think of as 9.8 newtons per kilogram, or we can think of it as acceleration of 9.8 meters per second squared. Now, this is on Earth. That's the gravitational field on Earth. And we can write this equation slightly differently. So the force of gravity is going to be equal to the mass of the object, in this case the sign, times that gravitational field strength of 9.8 newtons per kilogram. So now let's head back to our question. So we have our 10-kilogram object, and if we want to think about what's happening here, so we have this 10-kilogram sign hanging up. We need to figure out how much of it is pulling, what is the force that's pulling it down, and how much force needs to counteract that straight up to keep it in equilibrium. So let's calculate our force of gravity. Our force of gravity, remember I said, is the mass of the object times the gravitational field strength. And we know that the object is 10 kilograms. So we have 10 kilograms times 9.8 newtons per kilogram. And that leaves us with a force of gravity acting down on here of 98 newtons, and our direction for that is straight down. So this is the total force that the ropes need to balance. It acts only straight down, meaning the vertical components of each rope's tension has to equal or balance out that 98 newtons. So we know that we're going to need a y component. The two y components of these ropes, this tension, needs to equal 98 newtons straight up. Now, what else do we know about this? So we know that just like the wagon question from the last lesson, since the sign's not moving left or right, the x components of this force of tension have to be equal in both ropes. So we could say here that the tension in the x direction of rope 1 is going to be equal to the tension in the x direction of rope number 2. That's kind of the first thing we need to think about. Now I'm going to come back over here to the diagram and just add a little bit in here. So we know that each one of these tensions is going to have an x and y component. I'm going to move that 10 kilograms out of the way. So this will be my tension force in the x direction for tension number 2. This will be my tension force in the y direction for the tension of rope number 2. Now we need to know this angle here. And if you remember, this is where this geometry and remembering how your angles work. So if I have 72 degrees here, or 42 degrees here, this will also be 42 degrees. We're going to do the same thing on the other side. We're going to have a force of tension, a tension force in the x direction for rope number 1. And we're also going to have a tension force in the y direction for rope number 1. Okay, and this angle is 65 degrees. Okay, so now we've got some numbers, some angles we can work with, but we still don't know either one of the tensions. So in order for us to solve this question, we're going to have to rearrange to get one of the tensions to be a component of the other, expressed in terms of the other one. So let's think about what we've got going on here. So I know in the x direction that they need to be equal to each other because it's not moving left or right. The sign is saying stationary in the horizontal direction. So they're going to be equal to each other. That's what I've got going on here. So now if we think about the tension in TX2 or TX1, remember, is equal to the total tension cosine of the angle that's being made here, 65 degrees. That's what's going, so that's tension 1. And that's going to be equal to TX2, or my tension in the x direction from rope number 2. And that's going to be equal to the total tension in 2 times cosine of 42 degrees. So now I don't know either T1 or T2. I don't know the tension, so I'm going to rearrange. And I'm going to move this cos over here. And I'm going to express tension number 1 in terms of tension number 2 all over cos 65. Okay, so I'm going to express T1 in terms of T2, and now I'm going to use that to help me solve what's happening in the vertical direction. So in the vertical direction, so the up and down direction, I know that my tension on rope 1 in the y direction plus my tension in the y direction on rope 2 has to equal 98 newtons. And I know that it has to equal 98 newtons because the sign's not falling down towards the ground, but it's also not floating up towards the ceiling. It doesn't work that way. So I know that those two have to equal that force of gravity, that 98 newtons. This was the force of gravity. So now let's fill in what else we know. So I know that my tension in the y direction, remember this from yesterday, the tension in the y direction is equal to tension in rope 1 times sine now 65 plus tension in rope 2 times sine of 42 degrees, and that's equal to my 98 newtons. Now I'm going to express my T1 in terms of T2 so that I can solve. So T1 becomes T2 cos 42 all over cos 65 times sine 65 plus T2 sine 42, and that equals 98. I can pull a common factor of T2 out of both of these. T2 is equal to cos 42 all over cos 65 times sine 65 plus sine 42, and that equals 98. Rearrange and solve for T2. Remember, all of this is just a number. I can plug that into my calculator. All of that is just a number. So when we do all of that math, the tension in rope 2 is equal to 43 newtons. Now that I know that tension is equal to 43 newtons, I can determine what the tension in the other rope is. So remember, T1 was equal to T2 cos 42 over cos 65. And so substituting in for my tension in rope 2, 43 cos 42 all over cos 65. And that gives me a tension in rope 1 of 76 newtons. We don't need to recalculate the direction because we already know which direction it's going. We know that this is going straight up. So if we really wanted to, we would include, we don't need to calculate the direction. It's not straight up because they will be at the angles that we were given in the question. Okay, so now the other way that we can, so that's breaking it into its horizontal and vertical components, breaking it into its x components and its y components, putting it back together. Sometimes that means relating one to the other and expressing one as the other. Sometimes it means just breaking them into their component parts and adding them together. Now let's take a look at how we could tackle this if we made this just a single triangle tip to tail. So I have my force of gravity acting straight down. Here's that right there. We already calculated that at 98 newtons straight down. Now I'm going to redraw my rope 2, and I'm going to redraw rope 2 first. Here it is, and we know that it's at an angle of 48 degrees. No, we know that it's at an angle, of 42 degrees, which means this interior angle will be 48 degrees. I'm going to do the same thing now with my rope 1, because remember, vectors aren't locked in place. I can move a vector around so long as I keep the angle and the magnitude the same. So now we know that this one was 65 degrees from the ceiling, so that means that this interior angle is 25. By doing some math and knowing that 180 is the total, that lets me know that my interior angle here, my big angle here, is 107. Now I can figure out T1 by using my sine law. My tension in rope 1 is opposite to my 48 degree angle. So T1 over sine 48 is equal to my force of gravity here, so 98, all over sine of 107. Rearrange and solve, and that gives us our tension in rope 1 of 76 newtons. We can do the exact same thing for the tension in rope 2, or tension 2. So this time we're going to have T2 over its opposite angle, and its opposite angle is 25, so sine 25, and that's equal again to my force of gravity, 98, all over sine 107. Rearrange to solve, and that gives me tension in rope 2 of 42 newtons. So 2 ways to solve that question. You can choose which one you want. There's no right or wrong way. It's just whatever you feel works best for you. Okay, so let's look at one more problem. Let's look at a ramp problem. Before we start this ramp problem, though, I want to make you all familiar, if you've not taken physics, with some of the symbols that are in here, including the normal force and the force of friction, and how they relate to each other. So imagine that you have a box sitting on a flat surface. We know that the force of gravity acts straight down. Well, every force, if something isn't moving or is moving at a constant speed, constant velocity, has an equal but opposite, or that equilibrium force that acts in the opposite direction with the same magnitude. For the force of gravity, when an object is sitting on a flat surface, we call that the normal force. This is the normal force. If I want to push something along with some force to make it move, so if I am applying a force in some direction, I have to overcome the force of friction. And the force of friction is directly related, that's this Ff, this is the force of friction, directly related to the normal force. In fact, the normal force, if the object, the force that you need to overcome in order to make an object move is the normal force. And that normal force is equal to the force of friction. So that's the one thing that I want you to think about here, is that my normal force will be equal to my force of friction. This normal force is also equal to my force of gravity. So my normal force is equal to my force of gravity. And we're going to put this now into context with a question on a ramp. So imagine that I take this and now I turn it and I start increasing the angle, increasing the angle that this is sitting on. So now it's getting to the point where I think you can see it will eventually get to the point where it's going to start to slide down. So here's the question. In order to keep a 250 kilogram crate from sliding down a ramp that's inclined at 25 degrees, the force of friction that acts parallel to and up the ramp must have a magnitude of at least how many newtons? Well, it needs to have a magnitude of at least the normal force, the magnitude of the normal force. The magnitude of the normal force, remember I said, is opposite to the force of gravity. But as soon as we put something on a ramp, you can see that this changes a little bit. So my force of gravity is still acting straight down. Here is my force of gravity. So that doesn't change. Even though I've tipped the object so that it's on the ramp, that force of gravity doesn't change. It still stays acting straight down. What we need to do in order to figure out how these other forces are in play with each other is to determine the force of gravity in the y direction and the force of gravity in the x direction. And it's this force of gravity in the y direction that's exactly opposite to my normal force. And that's the one that we're concerned with today. So remember, I can find the force of gravity in the y direction by using my force of gravity. So my force of gravity in the y direction is equal to my force of gravity times times sine of my angle. So now we need to figure out what is the total force of gravity. So remember I said the force of gravity is equal to the mass of the object times that gravitational field strength or the acceleration due to gravity. So we have 250 kilograms times 9.8 newtons per kilogram. That gives me a force of gravity acting down on this of 2,450 newtons. Okay, so that's the force acting downward, but not all of that is counteracting my normal force. My normal force is acting straight up. It's only the y component that's acting straight down. So now let's use this force to calculate how much of that is acting down. So we have 2,450 times sine of 25 degrees. So my force of gravity in the y direction is equal to 1,035 newtons. I've explained to you that that's also equal to the normal force, and that is the force of friction that needs to be overcome in order to be able to, that's the force that you'd need to overcome in order to start the box sliding down the ramp, which means that this force of friction needs to be equal to that. So we need a force of friction of 1,035 newtons to counteract the normal force to prevent, and the force of gravity to prevent this box from sliding straight down. Now, with these questions like this, I always do these in its components. I don't try and do them as tip to tail. I always do these as components. And so we break them down into their components. Okay, so that was it for today. I really just wanted to show you those two quick examples and give you a little bit of background information. So for the homework, there are some questions posted. There will not be an exit ticket for today. Watch for the assignment to be posted. Should be posted at the same time as this lesson is posted, and it will be due at some point next week. If you have any questions, feel free to send me an email.